the acceleration that something moving is experiencing, is calculated by using the formula. Acceleration equals final velocity minus starting velocity, divided by time. A few things to bear in mind. First of all, a reminder to copy this from the formula sheet when you need to use it. Don't try and do it from memory, because you need to get the v and u the correct way round and have everything in lower case in order to get the formula marks. Depending on your calculator, it also might be safer to put the v minus u part in brackets when you are putting the numbers into the calculator. And before even that stage, how do you remember which letter is final velocity and which is starting velocity? If you sing the alphabet to yourself, you will find that u comes before v. So u is the starting velocity and v is the final velocity. One of the highest accelerations of a living thing is that of a jumping flea, which on average accelerates at a rate of 1,000 meters per second each second. Ejector seats give pilots an acceleration of about 100 meters per second each second, about 10% of the flea's value, and pilots often get injured by this. Acceleration has the units of meters per second squared. Take a look at how this is written. If, say, a car is braking, then the final velocity v will have a lower value than the starting velocity u, and so the acceleration will come out negative. In some ways, acceleration as a quantity makes a bit more sense if you think of it as an influence, rather than just getting faster. Because, as we've seen, it is perfectly possible for something to be experiencing an acceleration and be slowing down. It's just that acceleration, or influence, will be negative. Here are some speed-time graphs for 3 different objects. Let's see if we can work out what is happening to each object. The first object has a speed that is steadily going up. Therefore, there must be a positive influence or acceleration acting on the object. The second object has a speed that is steadily going down. Therefore, there must be a negative influence or acceleration acting on the object. The third object has a speed that is just staying the same, constantly. Therefore, there won't be any influence or acceleration acting on the object. Another way of saying this is that AE equals 0. Now let's have a go at this crazy formula, getting the numbers from speed-time graphs. Actually, it's pretty easy. You might even enjoy it. It's one of the things I do if I'm bored one evening. Here's a speed-time graph for a car. Let us calculate the acceleration being experienced during each section. For the first section, where the car is speeding up, we're expecting a positive influence or acceleration. But to actually do the calculation to get a number, we need to read off the starting speed for the section, then the final speed for the section, and the length of time this section lasts for. Can you read off these values yourself before we show the working? Just like any calculation, we start with a shopping list. The only slight difference then being that we get the values in the shopping list from the graph. Did you manage it? Anyway, then we write out the formula, put the numbers in, do the maths, then remember that the final answer needs units. During section 2, the object is just traveling at a steady speed, so it's not accelerating, sort of by definition. But anyway, let's do the maths regardless, to show you that it works. So for the shopping list, the speed at the start of the section is the same as the speed at the end of the section. After writing down the formula and sticking the numbers in, we can pretty quickly see that the acceleration will come out as 0, which is what we expected. Groovy. Section 3 is the interesting section. Really take care with reading off the numbers from the graph. Make sure you get that u is 20 meters per second and that v is 0 meters per second. Also make sure that you understand why the time is 10 seconds. Go on, really take a look. Don't be lazy. The time for that third section starts at 40 seconds along and stops at 50 seconds along, so that's a 10-second duration. Copy the formula out, put the numbers in. Notice that the final answer is negative. That's totally expected. And remember units. Bish bash bosh. Here's a neat thing. The area under a speed time graph gives the distance covered. At National 5 level, the area under a speed time graph is always the shape of a triangle or a rectangle, and we know the formulas for the areas of these, although neither is on the formula sheet. So you need to know the formula for the area of a triangle and the area of a rectangle. Your maths teacher might have told you the formulas in a slightly different form, and that's fine. Go with what you know. For example, the area of a rectangle is sometimes given as base times height, or width times height, or length times breadth, or whatever. Go with what you know. What the hell is the practical point of this? When the space shuttle was coming into land, the touchdown speed was really big, and it took a long time to get rid of all that speed. Which runways around the world would be long enough to be emergency landing locations for the space shuttle? The area under the shuttle's landing speed time graph was found, and that distance was the runway length needed. The only runway in Scotland suitable for the shuttle was the Machrihanish runway on the Kintyre Peninsula. The Mull of Kintyre is quite a cool place to visit for a few days. The plane that lands on Beara, the most southerly mainland island on the Western Isles, has a much lower landing speed, and by finding the area under the speed time graph, it was discovered that a beach landing would be fine. Why not go and do it someday? Let us find the total distance traveled during this journey, from the velocity time graph here. Shape 1 under the graph is a triangle, so use the triangle formula. Although the scale is quite straightforward here, sometimes in the exam, the scales might jump up in twos, or something less straightforward. Area 2 is a rectangle. Check you understand how we got the time duration number. Area 3 is a triangle, so make sure you use the triangle formula to find the area under the graph for this section. Again, make sure you can see where the numbers are coming from here. Then, the total distance is just the distance of each of the sections added together. Let's do a quick revisit of this formula. Have a look at it and remind yourself what each letter means. Now imagine that you are an Olympic ski jumper, or at least in the performance team for an Olympic ski jumper. You want to be able to find the value of acceleration that the slope is giving to the ski jumper. How do we do this? Well, the formula tells you that you need the starting speed, u, the final speed, v, and overall time, t. This is the same situation, but a version that is done in a classroom. We still want to find the acceleration given to the thing going down the ramp. So again, we need final speed v, starting speed u, and overall time t. The starting speed u is dead simple. If we start at rest, then u is just 0. The overall time t is pretty simple too. We just time how long it takes the thing to go down the ramp, with a stopwatch. The final speed v is an instantaneous speed. The instantaneous speed through the light gate. So the light gate uses the small distance d of the length of the moving thing, the small time t through the light gate, and does the calculation that instantaneous speed equals distance divided by time. Or you might have to do that calculation yourself. Either way, you now have final speed, v, at the bottom of the ramp. So we are now in a position where we can put all those numbers into the acceleration formula.